Hello everyone, welcome back. Let's talk about another easy problem on Leetcode today. To sum Leetcode 1. It is one of my favorite problems because it is one of the foundational problems that serves as basis for solving more advanced problems. This problem is part of Blind 75, a curated list of essential coding interview questions. You can find the full list linked in the description below. Be sure to check it out. I have already covered this problem on my channel before, but I am sharing this updated video to provide better clarity and improved video quality. Now to the problem. In this problem, we are given an array of integer nums and an integer target, and we should return the indices of two numbers such that they add up to the target. We may assume that each input would have exactly one solution, and we may not use the same element twice, and we can return the answer in any order. Then in example 1, for the given nums array and target equal to 9, we will return the indices 0 and 1 because numbers 2 and 7 at these indices add up to 9, and hence that will be our answer. Similarly in example 2, for the given nums array and target equal to 6, we will return the output as 1 and 2 because the elements at these indices 2 and 4 add up to 6, and hence 1 and 2 will be our answer. And finally in example 3, the two elements 3 and 3 add up to target equal to 6, and hence we will return their indices 0, 1 as our answer. The simplest way to solve this problem is via brute force technique. In this method, we will loop through every possible pair of numbers in the array. So we loop through the array with a pointer I that iterates over each element, and for each element, we loop again with another pointer j that starts just after I, and at each step we check if sum of any pairs equals the target. If it is, then we will return the indices I and j as our answer. For example, for I equal to 0 and j equal to 1, we check if 5 plus 3 is equal to target equal to 5, and the answer is no. So we move the j pointer forward to check for the next pair. Now we check if the elements 5 and 7 at indices 0 and 2 sum up to target equal to 5, and the answer is still no. So we move the j pointer forward. Now we check if 5 plus 6 is equal to 5, the answer is again no. So we move the j pointer forward. Now for I equal to 0 and j equal to 4, the elements 5 and 0 sum up to 5. So we will return the indices 0 and 4 as our answer. Now this approach is simple and easy to implement, but it is inefficient because for each element we are running through the rest of the array, resulting in time complexity of O of n squared due to nested loops. Now the bottleneck of the naive approach is that it exhaustively explores all possible pair of numbers in the array. Instead, we can ask ourselves, what if we could reduce the search space instead of blindly looping through all pairs? And this is where sorting and binary search approach comes in. Once the array is sorted, we can select one element as we did in the brute force approach, for example, element 0, and for that element, instead of performing a linear search to find its complement, that is target minus number, in this case it will be 5 minus 0 equal to 5, we can take advantage of the sorted nature of the array and use binary search, which reduces the search time to O of log n, which is significantly more efficient than the linear search used earlier in the brute force approach, which takes O of n time. For example, now if we search for complement of 0, that is element 5, we can easily find it in O of log n time. But now we have a challenge that since the array is sorted, we lose the track of original indices. For example, for element 5, the original index was 0, but in the sorted array, the index is 3. So to handle this, we first pair each number with its original index. For example, 5 was at index 0, 3 was at index 1, and so on, and then sort the array based on the numbers. And then we iterate through each element in the array and search for its complement. For example, we started with number 0 and check if its complement, target minus number, that is 5, exists in the array, and here it does. But if it didn't, then we would have gone to the next element like 1 and search for its complement, that is element 4 in the array, and so on. And here, as the number 0 and its complement both exist in the array, we will return their indices, that is 4, 0 as our answer. Now the time complexity of this approach is O of n log n, because first we sort the pair of numbers, that takes O of n log n time, and then for each number in the array, we search for its complement, which takes O of log n for one iteration. But because we are doing it for n elements, it will be O of n log n. Hence the overall time complexity will be O of n log n. And in terms of space complexity, it will be O of n because we have to store the mapped pairs as a separate array. But note that there is a variation of this problem where instead of returning the indices of the pairs summing up to target, we just have to check if such pair exists in the array. In that case, we don't have to store this mapped pair and the space complexity will be O of 1. Another approach we can use once the array is sorted is two-pointer technique. So instead of repeatedly recalculating and searching for the complement using the binary search, we can use two pointers, left pointer and the right pointer. The left pointer starts at the smallest number at the beginning of the sorted array and the right pointer starts at the largest number at the end of the sorted array. And we calculate the sum of numbers pointed by the left and right pointers. For example, here the sum of the numbers is 0 plus 7 equal to 7. Now if the sum was equal to target, we would return the original indices of these two numbers. However, in this case the sum is greater than the target. So that means we have to find the next pair where the sum should be equal to target. So which pointer should we move? Since the sum is greater than target, we need to decrease the sum. And to achieve this, we will move the right pointer inward, that is to the left. If the sum was less than target, then we would instead move the left pointer inwards, that is to the right. And we repeat this process until we find the number that sum up to the target. Now, continuing with the iteration, the sum of the numbers pointed by these pointers will be 0 plus 6, which is 6, still more than target. So we move the right pointer inward. Now the sum of the elements is 0 plus 5, which is equal to target. So we will return the original indices 4 and 0 as our answer. Now the time complexity of this approach is still O of n log n, because first we sort the elements, that takes O of n log n time, and then when we use a two-pointer technique, that takes O of n time. But still the overall time complexity will be O of n log n. And the space complexity will still be O of n as we store the paired numbers with their indices. Now with the two-pointer approach, we have significantly improved on the brute force approach by reducing the unnecessary comparisons. However, the two-pointer approach still requires us to sort the array, which takes O of n log n time. Can we somehow solve this problem in linear time, that is in O of n time, without the need to sort the array? And the answer is yes. We can actually use a hash map for that. In case of binary search, we required the array to be sorted and finding the complement took O of log n time. But if we use a hash map, the elements don't require to be sorted and checking for the presence of the complement takes O of 1 time. This makes using the hash map approach faster and more efficient. The only downside of using a hash map is that it requires extra space to store the values. However, even in the sorting based approach, we already needed extra space because we had to store the original indices along with the sorted elements. So we can start iterating through the array from left to right, and at each step we calculate the complement of the current number, which is target minus number, and check if the complement exists in the hash map. If it does, then we return the indices of the current number and the complement. If it doesn't, then we store the current number and its index in the hash map for future reference. Now let's see this in action. First number we see is 5 and its complement, that is 5 minus 5 equal to 0, does not exist in the hash map. So we add 5 along with its index 0 to the hash map. Then the next element we see is 3 and we check if the complement of 3, that is 2, exists in the hash map, and it doesn't. So we add 3 along with its index 1 to the hash map. Then the next number we see is 7 and its complement minus 2 does not exist in the hash map. So we add 7 to the hash map with index 2 and go to the next number, which is 6, and check if its complement, that is minus 1, exists in the hash map, and it doesn't. So we add 6 along with its index 3 to the hash map. Then the next number we see is 0 and we check if its complement, that is 5, exists in the hash map, and this time it does. Hence we will return the index 0 for element 5 and the current index, that is 4, as our answer. Now the time complexity of this approach is O of n because the entire array is traversed only once. And for each number, we look for its complement in the hash map or insert it into the hash map, both of which take constant time. And in the worst case, we can do it for n elements, hence the time complexity will be O of n. And in terms of space complexity, it will be O of n because we are using hash map to store each number along with its index. Here is a quick code walkthrough of the algorithm we just talked about with Java code on the left and Python on right. First, let's create a hash map or dictionary in Python to store the numbers and their indices. Now, we will iterate through the elements in the array, and for each number, we will calculate its complement and check if it exists in the hash map. If it does, then that means we have found the solution. So we will return the indices of the two numbers, the index of the current number and the index of the complement stored in the hash map. Otherwise, if the complement doesn't exist in the hash map, we will add the current number and its index to the hash map for the future reference. And if the loop completes without finding a solution, we will return the indices as -1. However, this scenario shouldn't occur as per the problem statement. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.